the operators in Coulomb Branch for superconformal table.
Great. Yeah, thank you to the organisers for inviting me today. So I'm going to be talking about this recent paper I put out with Francesco, Alba, Cristoforo, and Sonkao about these heavy operators in n=4 superconformals. So first, just give a little introduction. So an outline of this talk. So I'll first construct an orthogonal basis of operators, which we call canonical operators. And this is all within n=4 superconformals. And we're going to consider the large charge limit of these operators. So that's when their conformal dimensions become heavy. And so we're going to consider correlators involving some of these heavy operators. And we're going to calculate these by a semi-classical analysis. And so what we find is that if you take this large charge limit, so these operators become heavy, then the theory maps to the Coulomb branch. And so we can assign a scalar profile to the scalars, so the correlators become easy to calculate. And so we'll show you this for 3 and 4 point correlators, and then we'll check our results using supersymmetric regularization. So that's the outline of the talk. So n=4 superconformals. I'm sure everyone is fairly happy with it. It's the simplest AFT. It has maximal single symmetry, so it's a good playground to test out new ideas. And in particular, as we'll see in this talk, you can do some non-perturbative things with it. So I'll show you a non-perturbative result we find. So within n=4 superconformals, we will consider these operators. So these are half BPS superconformal primary operators, and they're built out of the scalar fields. So there are 6 scalar fields, and you can package them with this null vector y. We can just consider this general package of 6 scalar fields. So this here, this TP, is the single trace operator. So it's just a trace over some number of scalar fields. So then we will define this new basis of operators, which we call canonical operators. And so we define it by, you take m copies of these single trace operators. So we take TP, P is some integer k. So we take n copies of these, and then we also have these other multi-trace operators of the same dimension. And so we choose these other operators in such a way that ensures orthogonality. So all these canonical operators are orthogonal with each other with different n or k. So we can calculate the exact expressions using supersymmetric linearization, which I'll cover a bit later. So these are the operators we will be considering. And in particular, so it's effectively tk to the n, and so we're going to consider the limit when m becomes large, which we call the large charge limit. And for 3 point correlators, you can just take that large charge limit because there's no coupling dependence. But for the 4 point correlators, you have to be careful because there is coupling dependence. So we use this specific limit of this. We keep the large charge TOF coupling constant. So that's what we define here. It's lambda. It's quite similar to the normal TOF coupling, where we've effectively replaced n, the ranking gauge group, with m, which is effectively the dimension of the operators. So when we say the large charge limit, it's bearing in mind that this lambda is being kept constant. So now I'll go through the semi-classical analysis of how we calculate these operators. So so as I just showed, we will consider correlators. There are two heavy canonical operators and either one or two light operators. Okay, so we can write the correlation function like this if you're actually doing the path integral. And if we take this large charge limit, so if we take m to be large, then this path integral is dominated by the saddle point. And so the saddle point equation is given by this. And so we want to solve this equation in the large m limit. So we don't actually derive the result. We don't quite know how to do that, but we claim a solution to it, which is that's good in some ways. So we claim that the solution to that saddle point equation is this scalar field. It's just a function of the space-time coordinates and these y vectors. And the kind of important part is this capital omega. So this capital omega is an n by n diagonal matrix, which with components only along the diagonal, and these are roots of unity. So what this means is that the correlator in this large charge limit, the heavy operators kind of source this background, which is given by this classical solution. In particular, this background brings the theory to the Coulomb phase. So this classical background breaks SUN to U1 to the k minus 1 times U n minus k. So k can be 3, between 3 and n. And so scalar fluctuations along the unbroken directions, these remain massless, but the modes in the broken directions, these gain space-time dependent masses. And if you want to think of this as like from the brain point of view, if you have all your brains together, then you have SUN. If you separate some of the brains, then you get masses which are the distance between the brains. So that's why the masses are given by this difference between these small omegas. But that's a slightly technical aside. So we get these modes which gain these masses given here. The masses have these quite simple formulae. So now that we know what the classical background is, we can now use that to calculate 3 and 4 point correlators. The 3 point correlators, so I showed it briefly before. So we're considering, so HHL means heavy, heavy, light. So there are two heavy canonical operators and one light operator. And so what we claim is that in this large charge limit, this is given by just the 1 point correlator of the light operator on the Coulomb branch. So we just say that this 1 point, this light operator, the scalar acquires this classical solution. And then this theta is not, it's just this saddle point modulus which you integrate over. It basically just removes, integrating over theta just removes any to the I thetas left in the solution. So that doesn't mean too much. So just an example of how this works. So I showed before the single trace operator, it's TP. And so if we wanted to find the 1 point correlator on the Coulomb branch, then all we do is we just literally replace these scalar fields with our classical solution of the scalar fields. So we have however many number of them it is, and then do the trace over that. And we can actually find a general formula doing this whole thing explicitly, and it'll be some hypergeometric. So that's 3 point correlators, and so now we can consider 4 point correlators. So in particular, particular, we take we have two heavy canonical operators and two light operators. So the light operators are these T2s, so it's just basically close to phi squared. And these are kind of, well, they're the lightest operators, and they're kind of special because they're in a stress tensor multiplet. So we consider these correlators, and so we can first separate this into a free part and a dynamical part. So this free part we can just calculate by width contractions. So the T is like curly T is the dynamical part, which is the kind of interesting part. So this is effectively given by a 2-point function on the Coulomb branch. And so we saw that in the classical solution there are these massless modes and these massive modes. So the massless modes will just contribute to the free term, but the massive modes, their propagators will be conformal ladder integrals. So from that we find that this T, this dynamical part of the 4-point correlators, is just given by this solution here. So where P is this ladder Feynman integral. So it's this very simple solution. And what's especially nice about it is that we can actually do this sum over L. So we can sum over all the loops. That sum is known, so we can do that sum explicitly, and so we get a result which is actually finite in lambda. So the lambda dependence is in the ms squared. We can do this sum and get a result finite in lambda. So that's actually a non-perturbative result. So rather than having it perturbative in lambda, we get this non-perturbative result, which is quite nice. And they're generally quite hard to find. I'll just give a little picture of how this kind of looks like. So at some order in lambda, this T is given by the product of two ladder Feynman integrals. So these red dots are the loops, and which you can integrate over. You've got heavy operators at x1 and x2, and your light operators at x3 and x4. And so what we find is that if you then sum over all these loop orders, then this can be interpreted in the semi-classical picture as two massive propagators between x3 and x4 in a background sourced by the heavy operators at x1 and x2. So it reduces a 4-point correlator down to a 2-point correlator in a deformed background. So that's our proposal of the solution. But we kind of now need to check it. So how we do that is we use supersymmetric localization. This dynamical part of the 4-point correlator, this T, if we integrate over that with a certain measure, we obtain the integrated correlator. And what supersymmetric localization is this way of calculating. You can calculate both 3-point correlators and these integrated correlators as matrix integrals, it's a very powerful technique where you can actually calculate these correlators. So what we need to do is just calculate these for specific values of n, and try and take n as large as possible and see if they kind of tend towards the solutions we predict with the semi-classical analysis. And we indeed find they do agree. So here I've got just one example of a 3-point correlator, and we choose n equals 4, k equals 3, and this light operator here. And so this blue is the ratio between our localization calculations and the prediction at large n, which you can, it's tending towards 1, but fairly slowly. In yellow, I've got the Richardson extrapolation of that, which is just a way of making conversions speed up. And yeah, indeed, you can see that it converges towards 1 a bit quicker. But yeah, we test this for various different, lots of different cases, and we find they all tend towards our predicted values. So it seems like the semi-classical analysis is correct. Okay, so that's what we do. So just to conclude, so what we have shown is that correlators involving a special class of heavy operators, so these are the canonical operators that we define. If you consider correlators involving these heavy operators, you can determine them by just assigning a classical profile to the scalars. And so this maps the theory to the Coulomb phase and breaks SUN symmetry. And so we show how this works for 3-point heavy light correlators and 4-point heavy light correlators. And then once we did that, we checked our results extensively using supersymmetric localization. Okay, so some potential future directions would be heavy operators that preserve less supersymmetry. So what we considered was half BPS, so that preserves half the supersymmetries, but maybe some quarter BPS operators would be good. I think they're useful for like black hole stuff, but I don't know too much about that. We currently don't know how to construct these canonical operators for a quarter BPS operators, but there might be some kind of analogous way. This is all for n equals 4, but it'd be nice to consider less supersymmetric theories, which is n equals 2. Again, we don't know how to construct these nice canonical operators in these theories. A lot of this semi-classical analysis has been done in n equals 2, for example. So it's fairly reasonable to imagine that this should extend to n equals 2 at least. But we just currently don't know how to do that. And then, final point, this is all done in the large charge limit. But great to go beyond the large charge limit. So one potential way of doing that, there are these other matrix models. They're not related to the supersymmetric localization matrix models. But there are some other kinds of matrix models which have been found for, I think, SE2 and SE3, where you can calculate these correlators. But we don't know any extension to those to SUN currently, but it seems reasonable that they might exist. And so if we could do that, then we can go beyond large charge. And if we can go beyond large charge, then we can also get if we can go beyond large charge, then we can also get other non-perturbative results, and consider the full tau coupling rather than just this lambda coupling. But we currently don't know how to do that either. But these are all future directions which might be exciting in the future. So that's all I've got to say. So thank you.
Any questions for Gus? Would you mind motivating the classical profile here against semi-classical, like why it takes the form it does? Because I guess you kind of just introduce it as an answer, that's all, and it works, it's great, but it's some kind of like physics intuition. How does the light looks like that?
That's a good question. I guess that's yeah, I think it is kind of just a guess as to what the solution to the saddle point equation is. So yeah, I'm not quite sure why it's that particular solution. But I guess the fact that it's just like diagonals along the matrix, that specific form means that it does go to the Coulomb phase, which is like, if it has to be a certain, the matrix has to be that kind of specific shape for it to go to the Coulomb branch. And I think there are some EFT arguments in like n equals like SU2 at least, which why you'd expect it to go to the Coulomb branch. So I guess it's kind of an extension of from like SU2 theories expecting to go to the Coulomb branch. If you then promote to SUN, then you're still expecting to go to the Coulomb branch. And that's kind of what it has to look like. But yeah, I'm not sure too much more beyond that.
Yes. Do you know if the this correlator or so focusing on the 4-point case, if you take that into like a different channel, so you have like heavy, light, light, heavy, would that be under the same amount of control? Independently of just one crossing symmetry.
Yeah. Yeah, I think. Yeah, I'm not quite sure how you calculate it beyond just crossing symmetry, but I mean, we do like the OP analysis of for the 4-point of taking like both the T channel and the S channel of T. And yeah, so we can find results for those. So I guess from that sense, you can kind of, there's everything you need to know about the 4-point.
It's just that that channel comes up in like the thermal field theory case where by this like eigenvalue thermalization hypothesis, people expect that the heavy, light, light, heavy correlator for very heavy and fixed lights will boil down to a 2-point function, like you were saying, also on a deformed background, but now where the deformation is just a black hole in the bulk, and people expect to read off like what that is if this hypothesis is true. So it just seems super analogous to what you're talking about.
Okay, yeah. No, that sounds really interesting actually. But yeah, I think the